Alrighty. Welcome to the last unit of AP Chemistry before we start the review for the test. This unit is all about solutions, and there's not a lot to it. It's actually fairly easy. There's a little bit of math you have to memorize, but most of it's stuff you learned in pre-AP or could have figured out on your own. So without further ado, let's dive right in, no pun intended, to solutions. A solution is a uniform mixture, meaning a homogeneous mixture, of two or more substances, and they appear as one complete substance. A solution does not have to involve a liquid. For example, the air you are breathing is a solution of a couple different gases. If you deal with any sort of alloys like brass or steel, those are solutions. So they do not have to involve liquids. However, most of the time that we'll see, there's a decent amount of liquids involved. That is, in chemistry, we deal with a lot of solution. When we deal with solutions, we often will be dealing with liquids, but it does not have to be a liquid. A solution is composed of two components, a solute and a solvent. Whichever is in least concentration is the solute. It's the dissolvee. Whereas the solvent is the thing that does the dissolving. So it's the dissolver. And no, neither of those words is a real thing. Solute and solvent are the words you have to use on the AP exam, but that's one way you can remember it. Solvee ends with an E, solute ends with an E. Or you can remember that solute is less letters than solvent. Whatever is in less concentration is going to be my solute. Whatever is in greater concentration is my solvent. The solvent's state of matter determines the state of matter of the solution. So for example, if your solvent is a solid, you will end up with a solid solution. If your solvent is a liquid, you will end up with a liquid solution. So if a gas is dissolved into a gas, you end up with a gas phase solution. An example would be the air you're breathing. If you dissolve a gas into a liquid, you end up with a liquid phase solution. So soda would be your example. If you dissolve two liquids into one another, you can get a liquid phase solution. Example, this would be antifreeze or any mixed drink. If you dissolve a solid into a liquid, like salt into water, sugar into water, you can get a liquid phase solution as well. An example of that would be seawater or Kool-Aid or tea. And if you dissolve two solids into one another, you'll end up with a solid phase solution. An example of these are alloys, such as brass or steel. The maximum amount of solute you can fit into a solution, into a solvent at a given temperature is its solubility. And when all of the molecules of the solvent are being used up, are surrounding the solute, you have reached saturation, meaning every single molecule is holding on to or is surrounding the solute. And if you add just one more atom, one more molecule of the solute, then you'll become too saturated. You'll become what we call supersaturated. And some of the molecules of the solvent will leave the solute they're holding and try to hold on to that one. We've graphed solubility in baby chem before this in what you saw as solubility curves, where if you are on the line, you have a saturated solution in 100 grams of water. And since water has a density of 1, this could also read as 100 milliliters of water at each of those given temperatures. So at 0 degrees Celsius, 100 milliliters of water can hold 180 grams of sugar, or about, let's call that 110 grams of, I believe that this is sodium bromide, and so on and so forth. So if at 0 degrees Celsius I have 180 grams of sugar in 100 grams of water, I have a saturated solution. What if I have 181 grams? Well, that means I have too many grams of sugar in my solution and I am super saturated. You can think of these as kind of like a party. All right, if I have a party at my apartment is rather small and can only hold 50 people if I'm lucky with one bathroom. It would be awful. But if I have a party and 50 people come, my apartment is saturated. There is no more space at this party for anyone else to come through the door. We will be on top of one another. But if one more person comes, let's say you come and try to crash my party, well, if 50 people are in here, you aren't going to be able to make it through the door. You would have to wait until someone leaves. You would have to precipitate out of the party. You would be waiting outside until someone left. When you are above the line, that means that we are super saturated. So whatever is above the saturation, whatever is above the line, is going to precipitate out. How much precipitates out? You just count back down until you get to the line. But more likely, if I throw a party and I have 50 people in my apartment, I'll be lucky if 5 show up. Yes, it's a sad life of a teacher. So if I throw a party, 5 people show up, my apartment can hold 50. I am below my saturation point. So we would call that unsaturated. So when you are below the line, you are unsaturated. So if I have, at 0 degrees Celsius, if I have 100 grams of sugar in solution, that sugar is going to dissolve into the water and I will be below my saturation point. If I add more sugar, I can add how much more? I could add up to 80 grams more sugar. So again, a saturated solution is a solution that contains the maximum amount of solute that will dissolve under a given set of pressure and temperature conditions. You increase the temperature, you increase the pressure, that's going to affect your solubility. Saturated solutions are at a dynamic equilibrium with any excess undissolved solute, meaning that if some more comes in, it's going to upset that equilibrium and shift it one way or another. And since it's at equilibrium, the solute is both crystallizing and dissolving at equal rates. If you are unsaturated, then you're below the line on a saturation graph. The solution contains less than the maximum amount that can dissolve under set conditions of pressure and temperature, and can absorb more or can dissolve more. If you have a supersaturated solution, the way that this usually works, the way that you can make a supersaturated solution, is to elevate the temperature and then slowly cool it. So for example, if I add 220 grams of sugar to 100 grams of water at 30 degrees Celsius, so I'm here. If I gradually cool the solution down till I get to 0 degrees Celsius, I will have a supersaturated solution. I'll have 220 grams of sugar in 100 milliliters of water, which is supersaturated. And if I cool it very, very slowly and do not disturb the solution and don't have anywhere for the solid sugar to collect, I can make a liquid that has that 220 grams. If you ever buy simple syrup is a supersaturated solution of sugar in water. So all of these solubilities are in grams. However, you can also have molar solubility, and that's simply the number of moles that dissolves in exactly 100 milliliters of a solvent. So we often just symbolize this with molarity or the brackets. I had a feeling you'd be able to figure that out on your own. Molar solubility is moles of a solute per liter of the solvent. There's also 2 other vocabulary words that go with solutions: miscible or immiscible. Sometimes they're pronounced miscible and immiscible. They're just fancy ways of saying soluble and insoluble. If something is miscible, it means that it is soluble. If something is immiscible, it means it's insoluble. If you have something that's immiscible, The unsoluble part is called the emulsion and can be separated using an emulsionary funnel, which I'll show you in class most likely. Now, how much solute you have in a solution is its concentration. Concentration is how much stuff you have in a set amount of space. So, for example, we could take the concentration of our classroom. In our classroom, in one classroom, we have 11 students. So the concentration of our classroom is 11 students per classroom. So it's amount of stuff per space. In chemistry, we don't specify volume in classrooms, we specify it in liters. An amount of stuff is symbolized by number of moles in chemistry. So our concentration is going to be moles per liter, and we call this molarity, where molarity is moles of solute per liter of solution, and that is of the total solution. So I can tell you as a teacher, we try to trick you and make you think, oh, well, I only have 100 liters of water and I'm dissolving this 10 milliliters of hydrochloric acid in it. What is the molarity? Don't get fooled. We're trying to be sneaky. If I add 10 milliliters of acid to 100 milliliters of water, I'm ending up with not a 100 milliliter solution. I'm ending up with 110 milliliters. Sneaky, sneaky, Coach L. Now think back to gases and some of your basic principles of temperature. You know that when you heat something up, it expands. So volume in molarity can change. Number of moles can stay the same, but if I increase the temperature or I decrease the temperature, my volume will shift accordingly. So molarity actually is temperature dependent. So as chemists, we found that out and said, well, that's not very accurate. Let's come up with something that's a little more accurate. So we have a different unit of concentration we call molality, where molality is moles of solute per kilogram of solvent. And if you had me in baby chem, I teach this to my baby chem kids as saying, okay, molality is capital M, molarity is capital M, molality is lowercase m. What do we usually use lowercase m to symbolize? And they all go, oh, it's usually mass. Now, yes, it is usually mass. So molality is lowercase m and takes into account the mass of the solvent. So it would be moles of solute per kilogram of solvent is our molality term. So you can have something that's 12 molal. Yes, I just found that out. I thought it was neat. So you can have something that's molarity, and you say, oh, it's certain amount molar. And when you have something that's molality, you say, oh, it's certain amount molal. Almost as much fun to say as it is to write. We can also express concentration in the grams of solute per gram of solution, and as a percentage. We call this the mass percent. Sometimes you'll see it called the weight percent. Please, please, please don't use weight percent in your writing. This is an archaic term. The difference between mass and weight is that your mass is how much stuff there is. Your weight is that stuff, is this gravity's effect on that stuff. So I would highly recommend that you take the word weight out of your vocabulary for the AP exam and you write mass. Whenever you think weight, you should say, no, it's not weight, it's mass. We don't deal with gravity in chemistry because gravity is negligible on the subatomic scale. So we only deal with mass. Please don't say weight percent. So the mass percent is the percent of grams of solute per grams of solution. So this again is of the solution. So you're going to have to take the mass of the solute and add to the mass of the solvent, and that's your mass of the solution, and times 100 because it's a percentage. Lastly, mole fraction. Well, second to last, I have one more little tidbit. Mole fraction is a ratio of the number of moles of one component to the total moles present. So if I want the ratio of sodium in salt water, sodium chloride, and water. I would find the number of moles of sodium chloride, because that's going to equal the number of moles of sodium, and I would divide by the total number of moles. So I would add up the moles of water, the moles of sodium, and the moles of chlorine, and add them all together, and that's my sigma moles. That's the total number of moles on the bottom there. So we symbolize this with chi sub whatever it is we're talking about. So this, if I was doing sodium in salt water, this would be chi sub Na equals the moles of Na divided by the total moles of everything. So the moles of whatever you're talking about divided by the moles of solution, and you have to add up each individual component. Lastly, as a term for those that are going into the medical field, is normality. Normality is really used in acid-base chemistry, where normality equals the molarity divided by the equivalency factor. The equivalency factor is simply how many hydrogens an acid will give off, or how many hydroxides an acid would give off. So let's say you have sulfuric acid. Sulfuric acid is we'll pretend strong acid for right now, would donate 2 hydrogens, produce 2 hydronium ions. So you would take the molarity, let's say that the concentration of sulfuric acid was 1, we would divide by 0.5, we would divide by we would divide by 0.5, sorry, the normality fraction, the equivalency fraction is 1 over the number of hydrogens produced or hydroniums produced. So we divide by 0.5, we would end up with a normality of 2 for that solution of sulfuric acid, of 1 molar sulfuric acid. It can also be used in electrochemistry, where the normality, the equivalency factor is 1 over the number of electrons, or also in precipitation reactions, it's the 1 over the number of ions produced. That's the hard way of doing it. Normality is really just the molarity times the number of electrons produced or the number of ions produced. This is used in the medical field, however it is on the ways out. So you may not see it by the time you finish your nursing program or med school degree, but I wanted you to at least have experienced it. It is not particularly on the AP exam. Does it hurt you to know it? No. And that is a basic run through of solutions.